Let's give a final statement about the structure of nonlinear systems controlled by two fields, or with the presence of two fields, one drift vector field and one control field. The drift vector field is supposed to drive the system when there is no control. It sort of navigates freely without any possibility of being controlled. And that's why we call in the presence of another field that we can modulate in order to alter f so that we can conceivably visit any neighborhood point of the operating point by means of appropriate control actions. So we saw that when the system exhibits a scalar output, here x is an element of Rn and u is an element of R, and of course y is a scalar output. We saw that given an arbitrary infinitely differentiable function of x, we call those functions C infinity to indicate that they are continuous and they are continuously differentiable an arbitrary amount of time, so that we don't have to worry about the number of differential orders that we can obtain on some of the quantities that are present here. So when we have an arbitrary output, we saw that there is a natural linear system associated with that particular output. And that linear system is a subsystem in general of the system of differential equations, only that it looks linear in different coordinates. And those coordinates are generated by the gradients of this quantity and associated with gradients of this quantity and Lie brackets of those quantities. So what we're after in flatness is to find, not to, given an output, see how many dimensions the system can be linearized, but given a linear system, to find an output, given a system like this, which is linear in the control, can we find an output function which has a complete linear structure hidden in these coordinates and that can be exhibited under a change of coordinates. So what we saw in this particular case, in which h is a given function, is that we can define a set of coordinates C1, C2, CR, and these new coordinates is a partial definition of a partial number of coordinates, because the number of coordinates here is n and here is r, and we're assuming that r, at least for now, is strictly smaller than n. And this C1 was just the h, LF of h, all the way up to LF r minus 1 of h. And this is a function of x. So it defines a map which is at most full rank R, but it cannot be full rank N because it doesn't have N components. So this is only a partial linearization. We saw that this set of coordinates is nice to exhibit that linearity. And of course we can complement those coordinates by some other independent coordinates. Let's call them eta 1 to eta n minus r, so that in total we have n new coordinates, which are just arbitrary functions of x and possibly u, but it will suffice to define them independent among themselves and independent of these r privileged coordinates, so that the whole set C and eta, the whole composite vector of C and eta, conforms an invertible state coordinate transformation, so that we can say that C and eta can be characterized as a as an invertible differential map from this n-dimensional space to this n-dimensional space. We call this a diffeomorphism. A diffeomorphism will be a map which is differentiable and invertible, and the inverse of the map is also differentiable. So it's a nice one-to-one map between the original coordinates and the new coordinates. Some of them are distinguished because they sort of exhibit, as we will see immediately, a nice linear structure. And what we saw with this is that because none of these depend on u, they only depend on x, we can show that the derivative of the first coordinate would be the directional derivative of h in the directions of f and g. But in the direction of g is going to be 0 because it doesn't depend, those derivatives will not depend on u up to the rth order or r plus 1th order derivative. So all these coordinates, when you take the derivatives, they don't depend on u. And for that, we found that we had to have the following conditions. Lg of h had to be 0. Lf of Lg of h had to be 0. All the way to Lf r minus 1, r minus 2, Lg of h, all of them had to be 0. So, and the last one, Lf of r minus 1, Lg of h, was different from 0. This was what we found imposing the condition that this output y had to be relative degree r. So in fact, this is the definition of relative degree. A system like that with this output will exhibit a relative degree r for the output if all these functions are 0 except the last one that we call the controllability parameter. That will be the only function that links the control to the state. The rest of the previous functions don't have the possibility of influencing the state because the control is blocked by that condition. So if we derive with respect to time c1, we will have only Lf of h because Lg of h is 0. So c1 will be c2. And the same c2 dot will be Lf square plus Lglf. But Lf square will be just the next condition, and the other one relating to u will be 0. So we'll have that as a new coordinate. And therefore, we can proceed without finding any influence of the control all the way up to the r minus first derivative. And the derivative of CR will depend on this. When we take one more derivative, we will have the next Lie bracket LFR of H plus LG. I'm sorry, I made a mistake here. It's LGLF. It's LGLF. Sorry for that. LGLF R minus 1 H of X times U. So that will be the structure up to that point, and from there on, the equations will not have any particular structure. They will be just a nonlinear function of eta and possibly of u, possibly, because we can also eliminate that dependence on u if we want. By just choosing with enough freedom these n minus r coordinates, which are independent among themselves and also independent of these ones. So by redefining my control input as an auxiliary new input v, what we obtain is a nice chain of integrations up to order r, and the rest will be the zero dynamics. This is called the zero dynamics. So this is a structure, and given this output function, we can expect the existence of some r between 1 and n that satisfies, for the nonlinear system, this particular structure, and in fact the output will be just the first coordinate C1. So it's a very nice clean structure in which you have a linearizable part and a non-linearizable, not necessarily linearizable part, which might or might not depend on the control input. That's up to a choice. So with this structure, we can now ask ourselves the question, well, what would be a nice smooth function, infinity function of the state, which would enlarge the linearizability of the system to the fullest order, I mean to order n. Would there exist such a smooth function that allows me to do that? Well, certain conditions have to be met, and the way we arrived here, without saying so, is that intrinsically there is some geometry that we are exploring, and that geometry is the geometry of the distributions associated with f and g, and those distributions will tell us the possibility of having a full new set of coordinates which completely linearizes the system. And for that we simply remember the following thing that we said in the previous lecture. Let's assume that LGH is 0, and as we defined the Lie derivative along the Lie bracket of f and g of h as LF LG of h minus LG LF of h, this Lie bracket sort of measures the lack of commutative of the directional derivatives along the two directions represented by the vector fields f and g. So that kind of lack of commutative creates a new vector field representing a new direction in which we can go using f and g. G spans a one-dimensional subspace of a tangent space, and f also spans a one-dimensional subspace of a tangent space. If we start adding them, if we add them, we might obtain, if they are linearly independent, we might obtain a two-dimensional tangent space, subspace, and by taking Lie derivatives of f and g and repeatedly in any order, we will start filling up the possibilities of paths leading me from the operating point to points in the neighborhood of that operating point, so that the control is able to influence the system to visit those neighboring points. And for that, of course, this Lie bracket is involved, because it's part of the new dimensions in which we can travel, given that f and g only span a one-dimensional subspace, each one of them. F, for instance, can span a whole line starting from the operating point, positively and negatively, but that's all f can do. And g, which is the control field, can be modulated, of course, but will never come out by itself of this one-dimensional subspace in the tangent space. When we add them together, we start building up more dimensions. So now, if we take linear combinations of f and g, we will have surely the possibility of visiting a two-dimensional subspace of that tangent space. The idea of controllability tells me that I have to be able to generate enough directions, in fact n of them, using f and g, and all the possibilities of new directions that emerge from f and g. And what we saw is that this vector field is a new direction in which I can travel using f and g. So that is part of the thing that I have to consider. So here, in some respect, I am spanning a distribution which is not full dimensional, but only up to order r, And in this sub-distribution or subspace of the distribution, I can go in any direction I want because this system is linear and controllable. And being linear and controllable allows me to say that I can at least locally, by means of this diffeomorphism, visit all the points neighboring the operating point in X. So that distribution will come out to be associated with G, with Fg, and with all combinations of F and G and Lie bracket of Fg. And for the purpose of expediency, we will say that we can generate a distribution by taking iterated Lie brackets, fixing F and composing F with other Lie brackets of F and G. Of course, they might appear Lie brackets of G with F and G with F and G, and we will have just to use some of the properties that we saw about those Lie brackets to demonstrate that we can do away with this with this special set of brackets. These are going to span the distribution, which is very meaningful. So this was one of the conditions. The other condition was that LGLFH is 0. And of course, we have many other like that one that we would have to explore in terms of Lie brackets. So if something like this is 0, okay, this equates this operation with this Lie bracket. But if this is also 0, then this will be 0. And this is the type of conditions that we will be replacing here, because this is a set of very difficult to analyze conditions. I will show you immediately why. These are, if I am trying to look for an H that satisfies all those conditions, the first condition is a partial differential equation is a linear partial differential equation, right? And it says that the directional derivative of H in the direction of G is 0. That's the first condition. But the second condition gives me something different. It tells me that the partial with respect to X transpose of LFH, which is the partial with respect to X transpose of partial of H with respect to X transpose F, this is an object which is much more complicated. I would have the derivative of the first times the second, so I have this Hessian matrix, the Hessian matrix times F, plus partial of H with respect to X, partial of F with respect, in order to preserve the dimensions, I'll have to put partial of F with respect to X transpose as a matrix times the partial of H with respect to X as a vector. So here I have a matrix times a vector. Here I have a matrix times a column vector. So this is a set of n differential equations. When I equate this to 0, now I have a second order, and it's surely a second order differential equation, partial differential equation, which is much harder to solve than a linear partial differential equation. So these conditions lead to nonlinear partial differential equations very quickly, and that's what we want to avoid. And the way to avoid that is to bring in the possibility of going through directions which already synthesize some of the previous directions in a more compact manner and renders linear partial differential equations. For instance, if this is 0, and we have found out that the second condition gives that this is 0, then this has to be 0. So we start replacing those conditions by LGH equals to 0. That's fine. And the second condition will be LGLF of H equals to 0. But this being 0 means that this is 0, and this is already 0 because the third condition is 0. So L of Fg h has to be 0. And that condition summarizes the necessary partial differential equation that has to be solved into a linear partial differential equation. So to find h, I have to solve this equation, which is a scalar linear differential equation, because this is a new vector field which is known, and therefore I will have to solve only a first order differential equation, much as this one, very similar to that one, but along a different direction. So I start replacing those conditions by something which is much more doable, and I will have as a second, I will have something like this. The Lie bracket of f with f and g taken on h is equal to 0, and so on. Fortunately, there is a notation that we can use to abridge this. This is Lg of h. We replace this Lie derivative by something which involves f and g, and we call that L at fg of h. This simply means that this is the Lie bracket f and g. At fg is the Lie bracket of f with g, so this is replaced by that. And if we use it, it's much simpler, because this is partial of h with respect to x transpose times at fg. That means partial of h with respect to x transpose times fg, the Lie bracket of f and g. So that's a nice notation. And what would it mean to take another Lie bracket with f, for instance, to take the partial of L at fg of h with respect to x times f? Well, that's the directional derivative in the direction of f of or with g. If we want to take the directional derivative with respect to of that quantity with respect to x, that would be something like Lg of L at f g of h. And since this is already replacing that, this will be the next one, and the next one is just Lg Lf square of g. So we can compose those things and continue to redefine these Lie brackets along these new directions as directions spanned by this operator. And that's much simpler. And all of this will be 0, and all of them represent linear partial differential equations which don't have the inconveniences of this nonlinear partial differential equation. So we will use that. It's simply a matter of notation to be able to express the Lie brackets which are relevant in this set of conditions being replaced by some other equivalent set of conditions which render linear partial differential equations for the solution of h, and not nonlinear partial differential equations of higher orders. All of those differential equations will be first order when we use this. So that gives us an advantage, and this is the way to be able to extend this to n dimensions. If we ask that all these vectors satisfy certain conditions, all these directional derivatives satisfy linear independence so that they start spanning the tangent space, and also another condition that is very natural between vector fields is the involutivity. I mean, taking Lie brackets of any of those vector fields does not generate new directions that are already contained in that set. So this is something natural to be imposed on this set of vector fields g at fg at f square g. Linear independence to start growing the dimensions of the tangent space, which I can reach by means of control, the set of of controls that I can have access to, or the set of points around my operating point that I have access to, have a lot to do with that distribution, G add FG, add F squared G, and so on. And hopefully we'll be able to reach the state of add F G H n minus 1, and all those conditions are summarized into a single linear differential equation. The gradient of those things, the gradient of these things have to be independent, and multiplied by each one of these vector fields will give me a directional derivative. Will give me H. I'm sorry. Let me erase this. The gradient of H multiplied by this will be 0. Because this already contains the first condition, LGH, partial of H respect, that's the directional derivative along the direction of G, of H, that's that one, that has to be 0. This one is simply saying that the partial derivative of H along FG, which is this, is 0. So recall that this is just FG, this is F with F and G. So everything that I am imposing on this set of conditions that I erase here, that can be summarized here, lead me to a linear set of partial differential equations for H. This is what I have to solve if I want to find an H, so that this distribution spans the whole tangent space associated with the operating point X or P. Around that operating point, all these vectors point in different directions that are spanning that submanifold. And what I am asking is that H is sufficiently rich to have its gradient orthogonal to all those vectors. So H will have a gradient orthogonal to all these vectors, and this orthogonality condition is expressed by the fact that the Lie derivative, the directional derivative of H along each one of these vectors is 0. That's what these conditions for linearizability imply in the tangent space. I have to have a set of independent vectors which are all orthogonal to H. And as I add more and more, up to order n minus 1, all of them have to satisfy the same thing. But moreover, this sort of distribution will prove to be integrable. That means there will exist an H that it will integrate those vector fields if this distribution is involutive. That's Frobenius' theorem that tells you that you can have a solution of this first order partial differential equation provided that the directions taken by these vectors can be combined into vector fields and do not generate any new directions. So whatever vector fields I take the Lie bracket with respect to, they will obtain vector fields which are still found in the linear span of this set of vectors. So to generalize this condition, because what we have imposed here is basically LGH equals 0, LG LFH equals 0, all the way up to LG LFR minus 2H equals 0. This is what we have imposed here, to have this linear structure. But this is completely equivalent to LGH equals 0, LFG, right, of H equals 0, all the way to LF with F, and G, H equals 0. So that set of conditions is just LGH equals 0, L add F, G, H equals 0, all the way up to L add F, N R minus 1, H equals 0. So this is a much cleaner set of conditions. These partial linearizability conditions, by invoking the presence of the Lie bracket, given that it has a very nice relationship with LG and LFG and so on. So that set of conditions, which is equivalent to this set of conditions, can be written notationally, bringing the fact that f and g can be thought of as an operator which has very nice properties into a set of linear conditions, or linear, generating a linear partial differential equation for each one of the entries in this matrix. Each one of these is a column vector being multiplied by a row vector, and giving a scalar partial differential equation which is first order. That means it's linear. So that will allow us to replace this partial set of conditions by something that spans the whole space and really annihilates the presence of the zero dynamics. This is what's called exact linearizability, and that is the basis of flatness for this special case of systems. Is that clear? So that's the end of it. We will summarize all we have said in the following statement for that system. Associated with the system, then we will enforce the distribution. Let's call it delta G add Fg add Fn minus 1g. So this is a collection of n vectors. These vectors are vectors along which my integrating surface has to be a support of, or has to be tangent to all of those vectors, right? So this set of vectors has to be, delta is a linearly independent set of vector fields. It's a distribution. A collection of vector fields is called a distribution. So it's a linearly independent distribution. This distribution is given by this. And remember, add Fg is nothing but the Lie bracket of f and g, and add f squared of g is just the Lie bracket of f with f and g. So we continue to iterate the Lie brackets of f and g with f as many times as we need, all the way up to n minus 1. But that's one of the nice conditions. Okay, it has to be linearly independent in the sense that it can span the whole tangent space to my operating point. But in order to find the function that integrates all these vector fields, that means a function which becomes tangent to all those vector fields that I'm computing, I have to specify that all those vector fields belong to a plane which is n minus 1 dimensional, and that plane is just the distribution given by this. It's the span of that distribution. And there shouldn't be any new directions in the association of those vector fields with each other, so that I cannot travel outside of that plane, at least up to that point. So that will mean that this set of n linearly independent elements have to satisfy an involutivity condition. So this subdistribution G add Fg all the way to add Fn minus 2g, one previous to that one has to be integrable, in the sense that all these things have a support surface to which those vectors are tangent to. So that there is at least one extra dimension that will allow for the control actions. Remember that if I take only up to n minus 2, I am spanning fundamentally an n minus 1 dimensional tangent vector space, because here there are n minus 1 vectors. So at most I'll have n minus 1 dimensions, and the whole space, which is supposed to be Rn, will only have one free dimension. Well, that's the dimension in which the control has to enter, because we, aside from these conditions, that we will be imposing, there is the final condition has to be this, so that H has relative degree n. That means I'll have to take n derivatives of this function H to recently find U, and therefore this set of n vectors will define an invertible transformation. This is H. H is the output. LGH is 0. All these things are 0. So this will conform an n minus 1 dimensional subspace of the tangent space, and therefore the relative degree n assumption that I was looking for H is that this has to be different from 0. So this has to be involutive. This is a set of necessary and sufficient conditions for this distribution to be not only linearly independent and involutive, but to represent the possibilities of actually constraining to this tangent space all the internal dynamics and which has indirect access by the control, but the control only acts in this direction. So I can move in the state space from this point to the next, because the control will enter in this free dimension in the n-dimensional space. So this condition of being able to control the system in the last equation is represented by this one. And what it means is that along the Lie bracket corresponding to this expression, I will have a non-zero influence, and the control will be able to enter in the last equation. So those set of equations are very natural to define an input coordinate transformation, and that input coordinate transformation will be diffeomorphic, because all the gradients of these functions will be somehow independent. So this is what we need. Remember that the derivatives of H now have LFH. Y double dot was LF square H. Up to now, if I'm looking for that H which does not allow the presence of the control except at the last nth derivative, I will have here LF n H of x plus U LG LF n minus 1 H. So this is how the control will enter, and all these functions can be called now C1, C2, C3 nu coordinates, because they are functions only of the state, and I will have n of them up to this point. So if I take the derivative of C1, I will obtain LF of H, because it doesn't depend on U, so LG of H will be 0. Therefore, I will have C1 equals C2. C2 will be equal to this, because this is 0. So this will be C3, and Cn minus 1 dot will be Cn. And Cn dot will be just a function of x. And x now is the inverse map of C. So I have a complete state coordinate transformation that allows me to linearize the system by claiming that this nonlinear expression is just a new control defined in terms of the old control U. And the output Y is just C1. So I have, in essence, brought my system to this very simple structure. Cn minus 1 is Cn, Cn y dot is equal, y is equal to C1. So we'll have a nice chain of integrators from this auxiliary control input to the output y equals C1. So my system has V as an auxiliary input and a chain of integrations all the way to the output. If all these conditions are satisfied, that means that a set of conditions replacing those directional derivatives by the Lie brackets are satisfied. That means that I can find a solution to a linear partial differential equation for H, and that solution geometrically implies that this has to be linearly independent, and that this reduced set of vector fields reducing one dimension clearly tells you that there is a surface integrating all these n-1 vectors so that you have one dimension free to bring in all the nonlinearities of the system to the last equation. And the rest is just a linear chain of integrators. This is the geometry of feedback linearization. The existence of a smooth function H, whose level sets integrate this distribution and finds that this distribution is linearly independent. Those two conditions are unsuspected in linear systems, because we will see in a minute that this distribution is completely equivalent to the constant distribution representing the Kalman matrix. But this is automatically satisfied in linear systems because all these vectors are constant. So this will have no meaning in linear system, but in nonlinear system it sort of emerges out of the integrability condition so that we can leave a corner for the control to be able to act, moving this tangent space to different regions. And within that tangent space, I have the possibility of moving along any neighboring point of the tangent space, or the surrounding space of the operating point. So this is the essence of geometric control applied to the linearizability problem, which is an essential problem because it brings the possibility of using linear theory. We mean by that, all the machinery that is available in linear theory, like robust control, frequency domain conditions, into the nonlinear arena. If the system is feedback linearizable, then we will be able to use all that machinery in the local control of the nonlinear system. So the issue here is, of course, not every system will be feedback linearizable, but those which are feedback linearizable will enjoy this possibility. And we also call them flat. Flatness in this type of systems for scalar control inputs completely coincides with the feedback linearizability as long as the system has this simple structure. So these are things which are naturally tied to the concept of flatness in linear single input, single output systems. That will not be the case in multiple input, multiple output systems. So, any questions?
So the left linearizability defines flatness?
For this class of systems. It's not the same for this class of systems. Flatness applies to that class of systems. Nothing of this can be said for this class of systems.
So for a fine system?
For a fine systems, which is a very common class of systems, all this is completely equivalent to flatness. But not for this class of systems. You cannot do this analysis in this class of systems. You no longer have the simple structure. This is why differential algebra is needed in this class of systems. It's much more natural. It's more powerful, and it doesn't need any of these geometric pictures It's just algebraic properties of the field of variables that integrate the system, like x's and u's, or y's and u's, inputs and outputs and states. There is another completely different non-geometrical type of thinking that allows you to envision the linearizability of this system, but not here.
So the condition for the flatness for the Fan system is the distribution is linearly independent?
This distribution has to be linearly independent, and this has to be involutive.
So that's a necessary and sufficient condition?
The two of them are necessary and sufficient conditions, yeah. They constitute necessary and sufficient. Let me do an exercise, a simple exercise, so that you will have a feeling of why controllability is hidden behind all these developments.
So if they are not linearly independent, you find the rank is R.
Yeah, then you don't span the whole state, the whole tangent space, and you won't be able to go to certain directions.
So if that distribution is not linearly independent, so you find the rank R, and R is your relative degree?
Not really, because you also have to demand the corresponding involutivity condition for a smaller sub-distribution.
How do you find the relative degree?
Oh, I already said these conditions have to be satisfied. This is the definition, in fact, of relative degree.
Okay.
R minus 2 and then GLF R minus 1. These conditions have to be all zero. This has to be different from zero. That's the relative degree. And of course it has to do with this up to a certain point. Now you will have a subdistribution of dimension R, which is linearly independent, and the one smaller than that in one vector field will have to be involutive.
So if those two dimensions are met, then you then there's the H that exists to satisfy this condition.
That sort of partially integrates the vector fields, but you have left n minus r dimensions which are not accounted for in the approach. Okay. So let me give you a simple exercise in which I will show you the implication of this. By the way, Kalman's controllability condition, as originally derived by Kalman, is not the one you have in textbooks. Okay. I think it's for n equals 0, n equals 1, yeah, so on. Something like that. The original Kalman controllability condition was plagued with all these minus signs everywhere, but that is trivial to show that this matrix and this matrix have exactly the same rank. I mean, that's something elementary from linear algebra. So irrespectively of those signs which are appearing in the even positions of those column vector arrangements, it just coincides. The rank of this is the rank of this. But this was the original derivation. And we will let's particularize for a linear system, single input, single output system, in which we have the possibility of defining this vector C, which will get the system into canonical form. Incidentally, that canonical form that we had for the linearized system and for the partially linearized system are called Isidori's canonical form. And so if you have this, then your vector field F is simply AX, and your vector field G is just a constant vector. So that's a particular case of that. So it should satisfy all those conditions to be able to find the vector C, which eliminates the control from all the entries except the last one, and gives you this canonical form in nice pure integration form. So let's apply that. First of all, the distribution has to be G add Fg all the way up to add Fn minus 1g. That has to be linearly independent. And this has to be involutive. So what does it mean? What are the elements of that distribution? Well, G is just B. Now we have to compute add Fg. Add Fg is just the Lie bracket of F and G, right? That's the definition of add Fg. So the Lie bracket of F and G is the Lie bracket of Ax and the constant vector B. Trivially, this is just minus A B. Because it's the gradient of this, remember the formula for the Lie bracket Fg is partial of G with respect to X transpose. That's a matrix times F minus this matrix times G. All right? But this matrix is the partial of A, the partial of a constant vector with respect to X. That's 0, because B does not depend on X. So I'll have partial of F with respect to X. That will be A. The partial of this vector with respect to the vector X will give you the matrix A with a minus sign. And then you have to multiply that by B, which is G. So the first Lie bracket is just minus AB. So add Fg is just that. Who is add F squared G? And we will stop at that point. Well, that's the Lie bracket of F with the Lie bracket Fg. And here it will be the Lie bracket of Ax with the Lie bracket of Fg, which is minus AB. So the gradient of this is 0, times this is 0, minus the gradient of this, which is A, times this, it will be A squared B. Is that correct? Yes. So we're having that distribution is going to be like that. They have to be linearly independent. Well, that means that the Kalman controllability matrix is full rank. That's what you need to make the system exhibit that canonical form in which everything will look like a chain of integrations. Moreover, once you have that, what does it mean that this has to be involutive? Well, it means that a smaller set of this set of vectors, B, AB, all the way up to an AN minus 2B, has to be involutive. That's what this means. But involutivity with constant vector fields is trivial. The Lie bracket of any two vector fields here is 0. So 0 is in the span of this distribution and of this distribution, therefore is trivial involutive. The condition of involutivity means that any Lie bracket of this, or any two vector fields of this subdistribution, has to be a linear combination of the vectors which are already in there. Have to be in the linear span of this distribution. So that's trivially satisfied in linear systems. Therefore, a controllable linear system will always exhibit that pure integration structure in the controllable canonical form. Right? You will always have that. And in order to find the flat output, okay, which is what we're after in these lectures, remember the conditions that we had. We had, first of all, the linear independence of this distribution. Linearly independent. And we will have the involutivity of this. How can we find the flat output from these conditions? Involutivity of this distribution, linear independent of this larger distribution by one more vector. How do we find the flat output? Well, the output function that will represent the flat output has to be such that it must be orthogonal to all these vector fields except the last one. Because this is the only degree of freedom I will have to drive the control to the last equation and leave it there. And the rest will be free of controls and the functions of x in the nonlinearity. So hidden in that chain of integrators will be the fact that there exists an integrating function h such that the gradient of h times any of these vectors will give you a 0, and that h will also satisfy that the product with the last vector field is different from 0. Relative degree n of h, and this has to be true. So we can summarize that condition by saying that the gradient of that function I'm looking for multiplied by this matrix the gradient of that function has to be 0 for all these columns except for the last one, in which I'm willing to accept that this will be some function of x, a scalar function of x. Might be 1, might be anything. So the gradient of h will be given, if this matrix is linearly independent, then certainly that collection of vectors is invertible around the operating point. So the gradient of h will be proportional to the last row of the inverse of the controllability matrix. From this equation I solve for partial of h with respect to x, and you will have that the gradient of the flat output will be proportional by a proportionality factor which is completely arbitrary, proportional to the last row of the inverse of the controllability matrix. That's exactly the same condition we had for linear systems, only that in linear systems h is of the form C transpose x, and therefore when I take the gradient I obtain C as the vector C as the last row, or proportional to the last row of the inverse of the Kalman controllability matrix, and that will be the matrix C. So the flat output, which is C transpose X, is just the last row of the inverse of the controllability matrix multiplied by the vector X. So this thing derives immediately from the more general conditions. So that's it. Now all we have to do is examples and enjoy ourselves, because we know that if I can find a flat output which comes from this integrability condition using these formulas, then my nonlinear system is a linear system which is disguised as a nonlinear system. So the linear system will be just a chain of integrators of this form. I'll have a nonlinear function of c and a nonlinear function of c times u replaced by v. This will be non-zero locally at least, so I can invert this input coordinate transformation, and the output is nothing but the head of this chain of integrators. So in every nonlinear system I will have this hidden chain of integrators modulo an invertible input coordinate transformation in which the output is the nth integral of the input. That's the structure of any feedback linearizable and hence flat system. Any flat system in n dimensions of this form will be of this. Will have hidden inside it a linear system. It just takes a change of coordinates to uncover that linearity. And that change of coordinates is just given by we call that phi of x. All these are functions of x. And of course I have to have h here. H. So this is the coordinate transformation that will allow you to solve it. Incidentally, this has to do with the Lie brackets because we know that we can also involve Lie brackets in those directional derivatives. But this is the essence of feedback linearization and flatness for this class of systems which are nonlinear and n-dimensional. All we have to do now is to do examples.
So in the case of R as a relative degree, n minus R, those are the state that in a way hidden, right?
Yeah, it's a zero dynamics.
So why is it called zero dynamic, not hidden dynamics?
Because it's the same. They are called the same, zero dynamics or hidden dynamics, because the idea is that if you have if you have that dynamics, which is dimension n minus r, which is greater than 0, if you have that dynamics, when you do a feedback to partially linearize the system, that hidden dynamics will remain in the system without any control. Right. And therefore, it's an unobservable dynamics. Remember, this is like the observability matrix. It's also a good exercise to show that this is the observability matrix. Right, right. Why? Because H is C transpose X. Right. For a linear system, this is something that has to be done. For a linear system with Y equals C transpose X, H is C transpose X, LF of H is the gradient of this with respect to X, that's C transpose times F, which is AX. Okay? And there will be no U coming in because we are blocking those as we show. So LF n minus 1H or n minus 2H will be C transpose A n minus 1x, and n minus 2x, sorry, n minus 2, and LF n minus 1h is C transpose A n minus 1x. So really, all this in linear systems is just the observability matrix multiplied by x.
So if it's invertible, then you can calculate F.
Yeah, yeah. So the flat output, if it exists, has to be such that this set of maps have a gradient which is a full rank matrix.
Right. Then you can invert it.
And you can invert it, and therefore you can find x as a function of c.
Right.
And that will be the observability
I'm still thinking about the zero dynamic. Zero dynamic could be controllable, right? There could be a U in there.
Yeah, but you don't want to sacrifice the control of your system because you have a nice linear structure. All this effort was built to create a linear structure of reduced dimension,
Right.
so that you had a linear controllable system.
Right.
Then there wouldn't be any reason to do that if what you want to control is what is left from that.
Right.
But essentially, since that zero dynamics can be made independent of the control, it's an uncontrollable.
Or it's a system property, right? If the system could be, the zero dynamic could be controlled, influenced by the U, or it may not be. So that's a nature of the system, not something we can decide.
No, that's the nature of the transformation. We used to see it.
Yeah.
And remember, those transformations are one-to-one and known to. So no, these zero dynamics can always be made independent of U. Always.
Can always be.
Always. For linear systems,
Depending on your transformation.
it just requires a different transformation. Yeah, of that part of the system, the transformation that is fixed is the one that partially linearizes the system, but the other is completely free. And in general, when you transform those variables from the n minus r all the way up to n by means of a state coordinate transformation, in general, the control will appear there.
Yeah.
But remember, you're going to be using the control for controlling the linear part of the system, and so you no longer have a choice of control for the zero dynamics. That's gone. That's gone because you use that control to control the linear part. That was your effort. Your effort was to try to linearize the system.
Yeah, so there has to be a scenario where I don't need to worry about that part. I can use my control freely to control the...
Yeah, you're absolutely right.
Yeah.
The scenario is when that zero dynamics is globally asymptotically stable, then we can forget about it. But remember, this is not linear systems. You might have different kinds of equilibrium points. You can have stable equilibrium points in that part of the state space, or unstable equilibrium points. You can even have limit cycles. You can have all sorts of behaviors. And the zero dynamics is by definition something which is made a controllable. In linear system, that's clear that that's an uncontrollable portion. Incidentally, we can redo all these computations that we did here for linear systems, and we will obtain very nice, aside from the ones we already gave, some properties of the flat system in the linear context.
I just thought this is very illuminating because in controlling a physical system, I think there's always hidden dynamic. There's always some dynamics we don't know. And this perhaps help us to understand. For example, the two-man system, if we just control the motor side, consider it as a second-order system, then the load with the spring, that could be hidden dynamics, right?
Yeah, that's part of the zero dynamics.
Right.
Yeah.
Well, yeah,
It's hidden from the input-output relation that you want to control.
Right. So if I control the first mass and my control, I pretend that the second mass doesn't exist, but my control action will have an influence on the second mass.
Oh yeah, but you cannot control it because you're using your control to control the first one. The second one is going its own way.
Right. So in practice, under certain conditions, I can consider the two systems to connect it rigidly, so I can ignore it. But in other, when the spring is solved, this may help us provide the theoretical background to determine the threshold, under what condition we can consider it, and under what condition we don't need to consider.
Yeah, the two viewpoints that this allows you is you can consider that second mass as perturbation, and that's fine. You will have still a second order system that you can control. But remember, this thing is oscillatory. And it will be moving there because you're moving the the first part of the system. They are linear systems anyway. You're controlling the first part of the system without being able to control the second part. So the second part might start oscillating, and you will not see it from the first part because it's being firmly controlled by a force. But the thing is, if you, of course, here you can have dynamics that you have not modeled. That's not considered here. That's not part of my zero dynamics. In the structure that you do know of the system, and which gives you, let's say, a complete description of the system, is imprinted in this set of equations. That's all you have. If there is something else, you better put it here to be able to consider it. But some phenomena in nature cannot be put in here because we don't know about them. We ignore them. We have no knowledge about them. But this is all you know about the system, including all the strange behavior of parasitics and so on. You're supposed to have it here. If you have something else, then surely that's not part of the formulation. Or you would have to take it into account in such a way that now you bring in another dynamical system that is interacting with this one. And in that composition, you can also exploit geometry to see what else can you do to control the system and avoid problems from the part that you're not modeling explicitly in this. But that is true. So.
Take a break, Professor? Want to take a break?
Okay.
Or do you want to keep going? That's up to you.
Yeah,
Have some tea.
I'll have some tea.
Yeah.
Okay. Let me.
Maybe you can. You want to take a break?
Yeah, I'll take a
Maybe stop
2-minute break.
And so people can ask questions.
A car, a simplified model of a car, but without all the controls there, because we would need 2 controls to control the car. But here we will put 1 control because that's what we're doing now: single input, single output system. So suppose you have this model, and of course f is whatever is in the set of equations that does not contain u. So here you would have a constant scalar times cosine of x3 and a constant scalar times the sine of x3 and 0 here. And g would be something like 0, 0, 1, right? Because the control enters the last equation. This is the model of a car, but it's a very contrived model because the velocity is always constant. It's just always going forward with velocity v. What can you do to control the system to anything that you want? So g is something like this, and f is just this drift vector field, not animated by the control. So if you compute, so this is already a 2-dimensional distribution, and we have a 3-dimensional space. We need one more direction, right? And that direction might be fg. Let's see if fg gives me a new direction. I compute fg, which is add fg, the operator add fg, the joint operator, and it gives me this, which is proportional to this, except for, no, it's not proportional, sorry. So the distribution g add fg, if I compute add fg, is this, because if I compute the next one, add f squared g, it gives me a 0. So g add fg is this set of two vectors, and they span only a 2-dimensional subvector space. Therefore, g add fg cannot be involutive, because if you take the Lie bracket of g and add fg, you will not obtain not 0, but you will not be linearly independent. Let's say g is just 0, 0, 1, and add fg is the Lie bracket of f and g. And the Lie bracket of f and g is the partial of g with respect to all the coordinates times f minus the partial of f with respect to all the coordinates times g. So who is this gradient of g? If g is 0, 0, 1, this gradient is 0. It's a vector 0. So this is 0. Partial of f with respect to x will be minus v sine of x3. That's a matrix, right? It doesn't depend, f doesn't depend on x1, doesn't depend on x2, it only depends on x3. So in x3 you will have that. The second component doesn't depend on x1, doesn't depend on x2, depends on x3. and the third is 0, it doesn't depend on any of them. So this matrix is minus this times G, and G is 0, 0, 1. So when you multiply this, you get a plus V sine of x3, V cosine of x3, and 0. So you're reproducing in Fg is the same as F, right? I know it's not the same because this is V sine, this is V cosine. So is that a new direction for all the vector fields? You have V cosine, V sine, and then you have V sine, V cosine. So G at Fg represent two linearly independent directions, right? G and at Fg, because G is this and at Fg is that. But if you take ad f squared of G, you will obtain 0. So this thing spans only a two-dimensional submanifold of the three-dimensional tangent space. This system cannot be controlled. The accessibility distribution is not full rank. And moreover, it's not even involutive. When you take the Lie brackets now of G and ad Fg, you will obtain back some other expression, and therefore you won't have. The system cannot be linearizable by static state feedback. You know that in a car that you're driving with constant velocity, you have some sort of uncontrollability, right? You cannot go backwards. You cannot do many things. But when we have two controls, the story will be completely different. Okay, we learn how to find the flat output. It's very similar to the case of linear systems. The gradient of the flat output is proportional to the last row of the inverse of the controllability matrix. Right. That is a nice thing to have around because it reminds you of linear systems very much. I don't know if you can see this clearly, probably not. It's a robot with a motor and a link which are connected by a flexible shaft. So it's a nonlinear system. And when you model this using the Euler-Lagrange equations, you have 2 degrees of freedom because you have the angular position of the motor and the angular position of the shaft. And they don't coincide, they are independent. So you have 2 degrees of freedom, you have 4 differential equations. And the 4 differential equations are this one. This describes the link, which is like an inverted pendulum controlled by the elasticity of the difference generated by the angular difference between the motor and the shaft. When you have that difference, you create a torque, and that torque distributes in the position and velocity coordinates of the link. And the second equation is just a linear system in which you're controlling the motor. U is the input voltage, and you'll have something like that for the motor. It's also a second order system that generates this torque, and the torque is transmitted to the link, and there is some flexibility between them. Okay? So you have a fourth order system. Now, what would you do to find the flat output? You can do 2 ways. Either compute those distributions, but they become quite a task for systems like this and many others which are much more complicated, or you can find it by inspection. And it turns out that flatness can be always found by inspection. So the flat output, you can use those formulas if you want, and good luck with those. Or else you can actually see, and this is difficult to teach because it's part of a training. You say, well, I have to find at least one of the state variables, because the problem is that the flat output can be a combination of the state variables, and then it's much more difficult to see it in general. But what I'm after is to find some variable, luckily a variable already measurable in the system, which has relative degree 4. So let's try x3, for instance. If x3 I derive x3, I have x4. If I derive x3 once more, 2 times, that's deriving x4 once, the control appears. That's only relative degree 2. So x3 cannot be the flat output. Let's see if it's x1. Well, if I derive x1, I find x2. That's already, so one of the conditions, not relative degree 1. Keep differentiating, I find a function of x1 and x3. So that thing tells me at least this x1 is relative degree 2, and I can continue to differentiate because I haven't found the control yet. Take one more derivative, I'll have the cosine here times x1 dot. That gives me something back in this subsystem. But then I'll have x3 dot, and that x3 dot will incorporate x4. I haven't still incorporated the control, so at least it's relative degree 3. And take one more derivative, that will, the new thing will be to take the derivative of x4, and that gives me already the control. That's one way to do it, to start differentiating and see if you can find the control precisely in a number of steps, the number of differentiations that equals the dimension of the system. But that's to be lucky. The other thing is to ask yourself, well, if I knew certain variable, what else can I know? And it turns out that if you can know absolutely everything, then that's the flat output, including the control input. So why x1 would be the flat output? Because if I know x1, I know x2. Just take a differentiation of x1 to find x2. If I know x2, I already know x1, I can find x3. In terms of things that I know, which is x1 and x1 dot. Now that I know x3, I can know x4. And if I know x4, I can solve for u. So the flat output is x1. And that's found by inspection. Okay, you can do the other thing, but there are computer programs to do that. In fact, like Mathematica and those things can be programmed to do that. So in Maple, yeah. But you have to program that. And maybe there are packages over there that allow you to use them. So one of the things that emerges clearly from here is that x1 is the privileged output, which is related to everybody, because if I know x1, I can know every other variable, every state variable, including the control input. So I put x1 as my flat output. x2 will turn out to be just the derivative of x1. And x3 can be solved from here in terms of the second derivative of x1 and x1 itself. So I can write this equation for x3 from this second equation. And x4 is just the derivative of the previous thing. So I derive this expression, and I obtain three dots and the cosine multiplied by y dot and y dot. So x4 can be computed in terms of u, of y and the first 3 derivatives of y. And then u, it just takes the derivative of the previous one in a linear combination of x1 and x3. When you do that, you come up with an expression that gives you u in terms of y4 and a lot of other derivatives. So you have a differential parametrization of all the system variables and the control input in terms of y and y dot, y double dot, up to y4 dot. y4. So this is a differential parametrization. The last one gives you the input-output relation, and this allows you to see the things that you have in your system. This is a nicely behaved system, because you see from these expressions, if I were to drive x3 to 0, this is a stable differential equation. If x4 has to be driven from 0, this is just one derivative of the previous. So the input-output relation is right there. This is what allows you to bring into the attention of people that ADRC is very natural to be used in this class of systems, because from this expression you can simplify your system to a simple chain of integrators plus some additional disturbance, which is part of an endogenous disturbance generated internally by the system, by the nonlinearities affecting the system. And if there are some external disturbances, they will have to be considered here. But this is what allows you to immediately think of ADRC when you're doing flatness-based control. And moreover, you also think of linear control, because if you're willing to simplify your system, you will say this is the product of these two inertias divided by k times y4. And the rest I am going to call a disturbance or whatever. So the relation between y4 and u is just immediate across this constant, and whatever the rest of the nonlinearities are can be dispensed with if you want to design a nice controller to regulate y. But if you are interested in canceling all those nonlinearities, you can also do it from this control. You redefine your control in terms of all these nonlinearities and a new input variable v, and v will be just a chain of integrators, because you destroy these nonlinearities by canceling them from the control input. So if you define u as that nonlinear function, you define u as this plus all these nonlinear function, that gives you the possibility of redefining u equals v plus all those nonlinear functions, mbl I over k y double dot cosine of y plus etc., all the way up to mgl sine of y. If you redefine this like this, you put this in front of that equation, everything cancels, and what you're left for is that v is just ji over k times y4. So y4 is just k over ji times v. And the rest, and you concentrate on controlling this, and then you can find your original control. Once you find v, you can find your original control from here, if you're interested in canceling. But remember, canceling takes programming. Canceling takes wiring your experiment, so that you measure the acceleration, you measure including, maybe third order derivatives, I don't know, squares of derivatives. That's very involved. So you might know your system perfectly, but you're not willing to do all this either in your code, or you don't want to synthesize all that with your electronics. So you concentrate on the simple relation. You try to estimate that, cancel that, and control y. And controlling y is controlling everybody else, because y is the flat output.
So in Pistorius' approach to nonlinear system, he would cancel this, right? By feedback linearization.
Yeah, they mean nonlinear feedback of all these terms, right, to exploit the underlying linear structure.
Right. So that's the definition of feedback linearization, right? To cancel these terms.
Yeah, basically to bring the system to a chain of integrators in which, if you perform an input coordinate transformation like this, you obtain a clean chain of integrators.
Right, right.
Linear controllable system.
I found it very interesting, because that's the goal of ADRC.
Yeah.
But just a different way of doing it.
Yeah.
And also the feedback linearization is kind of misleading, because you are not really doing the linearization, you are canceling.
Well, but you're linearizing through exact canceling.
You cancel it, and you obtain the chain integrators.
Yeah.
Linearization could be you put it in the linear, you make it the linear system. You make a linear combination of y dot and so on. That's linearization. But this is more than linearization. This is canceling.
Well, it's canceling, but remember, it is exact canceling.
Yes.
It's not an approximate canceling.
Right.
It's exact canceling. You're getting rid of those things exactly. Well, that requires some very fine electronics, because you have to measure velocities, accelerations very accurately to be able to cancel them from here and let the linear integration structure of the system emerge as a simplified system like this. But you are canceling exactly, and therefore you're linearizing the system. This is why it's called feedback linearization, because through feedback, this is a feedback. You're feeding back the phase variables of the system, and you're redefining your control input to obtain a very simple structure in terms of the new control input. So you did feedback to cancel all the nonlinearities and to let the linearizing structure of the system, the linear structure of the system, without any approximation. This is very important. We're not doing any approximation. And therefore you have that. You have the linear predominance of your system. Another simple system is the Tora system. Is a translational oscillator. The Tora system is. This is a view from upside, from above. You have this mass here. You're viewing the system from above, and you have a spring here connected to something, and you have a pendulum here. A certain pendulum with a mass m, and you have an angle there, and you can. The way is, if this thing is oscillating, the thing would be, what can you do with the pendulum to dampen the oscillations? So this is an interesting problem because you have 2 degrees of freedom. You have x for the first mass, let's say m, and you have the theta for the second mass, so you have 2 degrees of freedom. That means you will have 4 differential equations or 2 differential equations of second order. So the first differential equation regarding the mass, the big mass, that is non-controlled. And the second differential equation describes the motion of the pendulum. That is controlled. It reflects the acceleration of the mass through here. So it's a nonlinear system because sines and cosines are everywhere. And you have some flexibility of the first mass being of oscillatory nature in its motions. These are 2 little wheels that allow this thing to move without much friction. So this thing is obtained directly by the Euler-Lagrange equations. And you can normalize this if you don't want to have those many constant arounds. You can just redefine your translational variable. You can define the time, redefine the time, redefine your control and put a new parameter epsilon. This will be the same system but normalized in the sense that this variable c is a dimensionless displacement, and the time is taken into account a natural oscillation time of the spring and the masses. That square root of k over the sum of the masses gives you the natural frequency of this oscillator. So you take that as a measure of time in terms of the original time, and your control, which is a torque, can also be scaled down in terms of k and epsilon and L. So you have a simpler structure, a simpler view of your system in a normalized manner. Normalization always pays because you can then you can change your parameters to your real case, and that will redefine, in this case, a single parameter that needs redefinition through some appropriate scaling that we have exercised here. So is this clear that this is the same as this?
Yeah.
It's just a redefinition of the variables, including the time, and taking the time of this oscillator as the natural time of the system. So the thing would be, from here it's not easy to guess what the flat output is, because if you say, well, if my flat output is C, I know this, but then I cannot solve this. This is a differential equation in theta, so I don't have to solve differential equations. Flatness allows you to parameterize all the variables without solving differential equations. So epsilon or C is not the flat output here. Theta is neither, because if you know theta and this, you have 2 unknowns here in these equations, U and C. So what is the flat output? It turns out that the flat output will be the center of oscillation of this thing. This thing moves horizontally, and the pendulum moves in a circular fashion. So at each point you can sort of project to one of the sides the position of the pendulum, and if you consider something like this, that will be the flat output. And that's the the coordinate, the horizontal coordinate of the center of oscillation. It's called the Huygens center of oscillation. It's a point. It's an immaterial point located beyond the center of mass of the big mass, and it's a projection of the pendulum position on the horizontal axis.
How do you find it?
Well, you can do it by writing the state equations and using the distribution formulas and the nonlinear Kalman controllability matrix to find it through its inverse. The other thing is by inspection, and since here neither C or theta are you try a linear combination, some combination of the two, and in this case it will be a nonlinear combination because it's a sine of theta. And you will see immediately that if you take the first derivative, well, you don't invoke anything because you're just constrained to obtaining velocities of displacement and angular velocity. Take a second derivative and now things start moving because you involve the equations of the system. And when you compute the second derivative, miraculously, you obtain that all this expression, when you substitute C double dot and theta double dot, you'll obtain that all this expression is reduced to minus C. So that's a beautiful sort of miracle because it says the second derivative is one of the original variables. So I can take two more derivatives of this variable and I will not find the control. In the first derivative, I'll just find y3 is just minus C dot. And one more derivative will bring in the control. Because of the form of the equations, you know that in here, I'm sorry, you know that in here, oh, what am I doing? You know that in here, the second derivative of C depends on the second derivative of theta, and theta already depends on the control. So you can take up to 4 derivatives of that flat output and until you find the control. So this system is flat. Why? Because you can reverse this differential parametrization and find all the variables in terms of y. Look, C dot is just minus y3. That's the differential parametrization of C dot. And now you know C dot, you know C dot. Let's see, what else can you, C dot is y2, sorry, C dot is y double dot. C is y double dot. C is double dot. C dot is the other state, this is the position of the big mass, this is the displacement. The position of the displacement can be differentially parameterized in terms of y, right? So you already know 2. Now you go for the third, now that you know C, and supposedly you know the flat output, you can know theta. And you can know it from here. Sine of theta, or theta is the arc sine. Theta will be the arc sine divided by epsilon of y minus C. But C is y double dot. So theta is a differential function of y. And theta dot is just the derivative of this. It will contain y3 3 dots. And u can also be computed because u will be a function of y4, which is this minus C double dot. U can be computed in terms of C double dot that you already have it from here. C double dot will be y4. You can compute, since you now know theta, you can know the cosine, the sine, all these terms, this and the velocity. You also have the velocity by taking one more derivative of that. You obtain everything, and you can obtain u as a function of 4 derivatives of y. So that system is flat, and the flat output is that one. So by redefining all of this expression by v, y4 is just a chain of integrations from v, And between u and v, you will have an invertible transformation that is valid between minus pi divided by 2 and pi divided by 2. Because cosine becomes 0 at at theta equals pi divided by 2, so you cannot go the pendulum, you cannot go move the pendulum in directions which are 90 degrees or above, because you have a lack of controllability there. So you can only turn in a certain region which goes from minus p divided by 2 to plus p divided by 2, and those are the motions that you can take to stabilize the system. So it's immediately clear that if you want to control the oscillations, for instance, you can do it from the flat output, because the flat output will drive the motions to 0. I mean, controlling y4 will control the acceleration, and controlling y4 and y3 to 0 will control the acceleration and the velocity, and controlling the acceleration of y dot of y will control the position. So you can damp out the oscillations in this. This is sort of also this is also a benchmark example that was placed to see what could you do to stabilize that system from motions of the pendulum. Oh, fortunately, this thing is very bad. This is the wheel inertia pendulum. It's a pendulum that has a big wheel here that can be rotated by means of a motor. Maybe you can.
Maybe you can expand it.
Yeah.
Is it better?
Yeah, much better.
Yeah.
So that's another example that was brought to attention, I believe, by the first time by Mark Spong.
Yeah.
It turns out that in the streets of a big city in India, I don't know if Bombay or something like that, people in the streets were selling this little toy. You can make this wheel, which is significant. You can turn it very fast, and what happens is, as a result of the conservation of angular momentum, you will create a torque, and the torque will rise the wheel almost by magic. And you can keep it up there with the motion of the wheel. So if you put a little motor here and build this in such a way that you don't have that much friction, you can actually control that system. But it has a singularity point, and this is what I want to bring to the attention of you. It will be clear from flatness that going through pi divided by 2 in this angular position will create an instantaneous loss of controllability. So that's something the flatness also reveals to you. What are the constraints naturally imposed in the system, which are not difficult to guess from the system equations? You see, you're given this set of equations for the system. How do you know there is a singularity there? It's not easy. So you have the Q2 represents the angular position of the wheel, and Q1 represents the angular position of the pendulum. So this variable Q1 is this angle here, and Q2 describes the angular motions of the wheel. This wheel has some inertia and a mass, and this is unactuated here. This is free to rotate here without any friction. So when you start moving this by conservation of the momentum, this thing will start rising up. It's like creating a torque here, artificially from here. So these are the equations that describe that system. The system has 2 degrees of freedom, because this link has a mass concentrated there, and this has M2 and has some inertia also. And this has also a moment of inertia, I1 and I2. So you have a complete system that, if you use the Euler-Lagrange equations, you will have this set of equations. It's a nonlinear set of equations. and the torque that you give to the wheel is the control input. That's what moves the wheel, and this wheel indirectly moves the whole system in the change of angular position. It's called the inertial wheel. It's a typical underactuated system because you have 2 degrees of freedom. You need one coordinate to describe this mass position, and you need another coordinate, the angular position, to describe the angular position of this wheel. So you have 2 degrees of freedom. And those 2 degrees of freedom give you 2 second-order differential equations which are coupled. So this is your system. And you have only one control. The control is the torque given to the wheel. And you can want to incorporate the motor. You can normalize this system. It's a system which is nice to normalize, even though the normalization looks kind of complicated because the time has this expression, and the torque has this expression, the normalized. But you get a very nice simple set of equations. If you normalize them, this is what you have. You have this weighted sum of the accelerations is given by this, which is sort of representing the gravity acceleration, and the given torque is distributed in accelerations of the link and the wheel. So it's a very nice simple system which is nonlinear. And from there you can get, by solving this very simple matrix equation for Q1 double dot and Q double dot, the angular acceleration, you will have the control entering Q1 and Q2 in those equations. So is Q1 the flat output? No, because knowing Q1 doesn't allow you to know. Knowing Q1 allows you to know U, but then you cannot find Q2 because you would have to integrate this. You have to solve the differential equations. Since you know Q1 and U, you don't know Q2. If I know Q2, I know the second derivative. I have two unknowns here. I cannot solve it. If I know Q2, I cannot solve for U or Q1 because I have too many unknowns. And if I know Q1, I could solve for U, but I cannot solve for Q2. So Q1 or Q2 are not the flat out. So it's some combination of Q1 and Q2. It has to be the center of oscillation. So it's a combination of Q1 and Q2.
This is very important.
And what you do here is, if you take a linear combination of the two angular motions, you will obtain a flat output because the first derivative of this is just the angular velocities, the weighted angular velocity. The second derivative, when you do F double dot, you will obtain sine of Q1. And this is an indication that you're in the right path because now Q1 can undergo 2 more differentiations before you find U. So F3 is this Q1 dot cosine of Q1. And you know that in the next one you will have Q1 double dot that already contains the control input. So that F is relative degree 4, and 4 is the dimension of the system, so that has to be the flat out. And you can invert this because if the acceleration is sine of Q1, Q1 is the arc sine of F2. And the derivative of Q1 is just that the derivative of the argument, F3 divided by square root of 1 minus the second derivative square. So Q1 and Q1 dot, the position and the velocity of the link can be obtained from the flat output. And you keep solving this equation. Now you know Q1 and Q1 dot. You go and solve for Q2, and it can be done. Q2 is solved from here. Q2 is F minus Q1, everything divided by epsilon. But Q1 is already found here, so everything can be put in terms of F and the arc sine of F double dot. And the derivative of this will contain already F3. So when you take one more derivative, you will obtain the control through the 4th order derivative of F. So the fourth derivative of the flat output will give you the relation with the control, and it's a hell of a nonlinear relation. It has all the nonlinearities there, and the relation between U and F4 tells you that, you know, behind all this algebraic garbage, you will have a direct relation between the fourth order derivative of F and U. And that's what makes the system linear and controllable and nice to work with. Of course, you might have a singularity here. The singularity, if this thing goes to 0, if F double dot goes to 0, that means, goes to 1, that means you'll have a singularity in the whole scheme. And F double dot equals to 1 means that Q1 has to be pi divided by 2. So at pi divided by 2, you will reach a singularity. And the system will locally lose its controllability, because this fourth order derivative is blown up and you can no longer be defined. So singularities was one of the specialties of Vladimir Arnold. He studied singularities in geometry from a general viewpoint. What somebody might do is in the context of this flatness, to see what that theory of singularity, which is very rich and very extensive, can give you in order to deal with those singularities in nonlinear systems. But you know, if you redefine this expression with F4 substituted by V, this gives you an input coordinate transformation, and F4 happens to be V. That's the chain of integration. The rest is the nonlinearities of the system, just surrounding, disguising my system as a nonlinear system.
So it seems there's a pattern here. That you, all these very interesting examples, you will have the two dynamic systems interacting with each other. You have two masses in different forms, different configurations, and and the key is to find the flat output. I don't know if anybody here pay attention to this. This is maybe the most critical step. Is how do you go from a general equation to the flat output? Maybe by this time you have a trained eye, but for us, for maybe there's some practice or some exercise we have to go through. But I think Jin Feng and especially Yu Dun, they all deal with two-mass systems. They're all interacting. Sometimes you have one control, sometimes you have two controls. But this is very valuable experience, examples how we know the Professor Jiang. How do we deal with this kind of system? So maybe in the next few days or a couple of weeks, let's concentrate on finding the flat output to this kind of system, right? So maybe you can learn from the master. Maybe there's, I think what I heard from Bingwen was she uses the maple to derive flat output.
Yeah.
But it was very complicated. Right? But this is much cleaner. This is go from the geometric and also physical properties of the top 10 flat output here. So maybe you can let us know some secret.
There's no secret. There is no secret. You got to try all the possible tricks.
So this is maybe after a couple of attempts that the F equals Q1 plus constant times Q2. That's
yeah, that gives you the flat. But by just looking at the equation and start taking these differentiations, you know you're in a good path when all of a sudden some higher order derivative collapses to the original generalized coordinates. Mm-hmm. Now you're in a good path, because that allows you to take more derivatives and the control will not show up. And that's what was done here. So this restriction is very clear. The acceleration of this immaterial point, which is a linear combination of the angular position, cannot be larger than or equal to 1. And it happens to be 1 precisely when you are in a rest-to-rest maneuver going from 0 to. But this is a singularity that has passed away very, very quickly. in real experiments. And you can plan your trajectory. Oh, this is terrible. This cannot be seen.
Just take it out of that mode, yeah. You can close it.
Yeah. Yeah, but this is how this trajectory is planned. Let me go through it quickly. We usually wants to bring the pendulum from an initial position in which this is in the downwards equilibrium, so Q1 is pi, and you want to bring it to Q1 equals 0 or minus pi to give a complete turnaround. So you are at an initial position that can be described by either pi or minus pi, and you want to go all the way up to 0. At a certain finite instant of time, you want to reach Q1 equals 0. That means your link will go upwards and stay at that equilibrium indefinitely. And but there is a singularity at pi divided by 2. We know that in this position there is a singularity. That's when the flat output, which is an intermediate point between these two angular positions, goes through pi divided by 2, goes through the maximum magnitude, and therefore you will certainly violate that constraint for linearizability. But that happens only in an instant of time. If you give it enough momentum, it will go through the singularity fast. And you lose controllability there, but you already gave it enough momentum so that it will reach the upper portion in a finite time and then go to the equilibrium. So if everything starts downwards, you know you're going through a singularity when you go up. If you start upwards, the thing would be to equilibrate this pendulum so that if you puck it, you will not destroy the equilibrium. So the idea is to have this the nominal value of the flat output should evolve in such a way that the second and third derivatives start all at 0 and end up at 0. So this is the velocity and the acceleration at this point, which starts at 0, has to end up at 0 if you want equilibrium up there. Velocity and velocity equals to 0 also in the final position. So if you propose f to be a straight line, you know that the first derivative is constant, the second derivative is 0. So the acceleration of those things will be 0, and this first derivative, which is a constant, can be brought to 0 too. So this is what we plan. We plan a sort of a straight line. That's what we're after for the flat output, an indefinite straight line. So and it will have to comply with the conditions that at t0 that should be 0. So Q2 correspondingly, this is the flat output expressed in terms of Q1, which is pi at the initial moment, and epsilon Q2, because this wheel will be turning, it will be at some position. You can find out what the initial value of this has to be from the initial value of Q2. It can be computed. So if this has to be 0, epsilon Q2 has to be equals to minus pi, and therefore Q2 can be put in terms of f. So you start analyzing the flat output and its time derivatives in order to find the conditions, the initial and final conditions, so that you can smoothly interpolate between them. And it turns out here that the flat output has to sort of satisfy a straight line equation so that the second derivative will start at 0, it will end up at 0, and the first time derivative will be will also have the same property of starting at 0. So you put a Bézier polynomial, and this is what you do. What you do actually is you integrate something like this. which goes from 0 to 0 in the acceleration to obtain something from 0 to a constant value in the velocity, and the integral of this will be a straight line with some smoothness here, with no discontinuities here. So you start planifying, and this is the nice thing about flatness. You can actually play around with this. The amount of solutions that you can find is immense, but as long as you find a good, sensible solution, like you know that you have to start with 0 acceleration and end up at 0 acceleration, and you can compute the rest of the variables from there. Like you can compute the position of the link corresponding to this flat output will give something like that, and also Q2. You can compute everything and the control input. You can control Q1, Q2. Here you see that you have a non-minimum phase phenomenon, and it will show clearly and you can pre-compute U, and you know you have some singularity at some point, and but that's the way it turns out to be. So the planification is pretty much interacting between the physics and the mathematics. You know what your initial condition, you know where you want to go, you know something that allows to relate everything to that flat output. So use that to advantage in order to exploit your objectives in terms of a feasible trajectory for that flat output. And that's what we did here. And of course the control will go through a singularity when just it comes to this position. The flat output will be going through pi divided by 2, and you have this big impulse on the control. That's a singularity. That shouldn't happen. That should destroy the motor. But what these people do is that they give it enough momentum and then release the whole thing and just go through in a single bound. And but that's something that you can explain physically from flatness. And of course, the whole idea is to do this input coordinate transformation. Remember, the fourth time derivative of f was here. You substitute that by v. And this is a recipe for your nonlinear controller. But from here, v is controlling a linear fourth order system. So that's trivial to stabilize that around the desired trajectory. And this is how you would compute the control, knowing that the second derivative is a function of the state, the third derivative is also a function of the velocities, and so on. So everything here is nonlinear functions of the states, because that's something that you have to realize. You don't want to use that variable in reality. You want to use what you can measure. And even though you can measure here that flat output, you also want to make use of your system equations. And this is the parametrization. You see, you will need all this derivative of the flat output. They are simple functions of the states. Like here, it's just the velocities. The acceleration is just that. You don't need to compute second order derivatives of f. You will just compute the sine of q1 of the first angle. And f3 is just the product of the cosine times the velocity, and so on. So everything can be placed back in the state if you want to do state feedback, because otherwise you will have to generate these functions, and they are already here. So use them. Use them, because that simplifies your feedback.
So can we understand it like this? We want to control Q1 and Q2.
You want to control the flat output.
No, the Q1, Q2 are the control objective, but we translate that into the control objective for the flat output.
Yeah,
right?
yeah.
So you compute the desired trajectory for Q1 and Q2.
No, you remember, everything has to be related to the flat output.
Of course.
So once you have the differential parametrization and the definition of flat output, you start saying, what I want to do with the system? Well, I want theta 1, the angle of the link, to go from minus pi to 0.
Right.
That's a single angle. So that's an objective. The wheel will be turning. Maybe I want to rest up here and stay in equilibrium, and if it starts going one side or the other, it will react and control the position. But that's a different scenario. The first scenario is you want to drive Q1 from minus pi or pi to 0 in a single bound. So that's your objective. But the flat output depends on Q1 and Q2. So now you start analyzing what's going to happen between the initial and the final point, or at the initial and the final point for Q1 and Q2. And the parametrization, because flatness is able to relate you back to the original states in this. Sorry that I have to go to this. This is what I explain in these pages. This is my objective. I start at pi or minus pi, and I want to go to Q1 0. So that's my final objective. And I have to do that in terms of the flat output. So the transfer problem has to be translated into a nice trajectory for the flat output. And what do I want? I want this angular combination to start at some value, 0, and to end at some other final value, but without any velocity. I mean, I cannot pass through the North Pole just passing and say goodbye. I want to stay there. And so I don't want to allow any acceleration here. And I want to have 0 velocity when I arrive there. That's a physical constraint. And that has to be translated in terms of Q1 and Q2 so that I can define F appropriately. So F star has to start at 0. So everything starts at rest. The pendulum is down, the wheel is stationary, it doesn't move. And now I'll give it the control so that it starts building momentum and it goes up. What I want at the end is not to pass through the vertical position, to stay there. So I need that the final velocity of Q1 be 0. Q2 will be turned. It would be nice if the motor stopped, but that the requirement is I want to stay here. So what does it take to stay there? Well, the physics tells you, and the analysis of this thing, from the initial value, the value of the flat output has to be pi, which is the value of Q1, plus some value of Q2. You might not know, but it's a constant value. The initial conditions are set whatever they are. This Q2 0 can be something, doesn't matter. It will be some value. So you want to start possibly growing this F has to grow linearly, because this is what tells you that this will give you 0 acceleration at the beginning and 0 acceleration at the end. And hopefully the velocity will start at 0 and will end up at 0. That's the implication. So by using the flat output, you start seeing that you have to, Q2 will be related to the velocity of Q2 is related to the velocity of F, and the position F2 is related to F. But the position of the second motor is indefinite in the sense that it can grow to infinity. I mean, we have had motors running for 20, 30 years, and those motors have an angle which is immense, billions and billions of degrees, and nobody cares, right?
So here, F star is given, or Q2 star is given? Which one comes first?
No, this you prescribe. This you prescribe on the basis of your physical thing. You want the acceleration of F to be 0 here and 0 here.
Right. So you prescribe F star.
I prescribe F star.
And that corresponds to a Q1 star, right?
That will correspond to an F dot and to F.
Right.
And from F will give me the initial condition for Q1, which is 0. Right. Will give me the initial condition for Q2, which will also be 0.
So the Q1 star is the prescribed motion for Q1, right?
Yeah, for Q1. But you can pre-compute this with the help of the differential parameterization.
So that's my question. Do you pre-compute Q1 star, or do you pre-compute F star?
F double dot star in this case.
So you start with F double dot star.
In this case.
And then you compute the Q1 star.
And I compute all this, and from this I can compute Q1 and Q2. And Q2. And Q2 will be also going from rest to rest. It will start at 0 and it will go to a steady velocity that produces. But
how do you know the F star you pre-compute is physically possible for Q1 star and Q2 star? No, not physical version.
Well, you propose that, and you examine the differential parameterization to compute Q1 and Q2,
right.
And you see that it remains finite. Q1 and Q2. Q1 depends on the acceleration, and Q2 also depends on the acceleration. So it's nice because the second derivative of Q1 will be 0 here, it will be 0 here. So the velocity will go something like this. The velocity is constant, and then it will go down and go back to 0.
So the speed and acceleration at which Q1.
Yeah, that's another degree of freedom.
That's physically possible.
That's another degree of freedom.
Yeah.
If you try to do this very fast, probably everything will blow up, or you will see that the accelerations are very large and that the control cannot cope with that. So you start planifying. This is what planifying means. Planifying is done usually through, you make a proposal for planning, and you see the consequences, and here you can actually compute those consequences in your state variables and your control input. You see that that's not convenient? Well, you change your planning, and here you can change not only the magnitudes, but also you can change the stretch of time. You can stretch the time and say, I want to do it very fast, not so fast, slower. You can do that from here and examine what the implication of those changes is in your positions and your control. So this is, with this technique, you have access to actually examine your initial proposals and modify them as to fit them to suitable restrictions of reality. This is what it is, and but of course, sometimes you have to go through a singularity because there is no way around, and the singularity is just built in here and here. You see that from the equations. That's something that this allows you to see immediately. You say, wait a minute, well, what does it mean that the sum of these accelerations shouldn't be 1? The sum of those accelerations, this is a normalized thing, shouldn't be the acceleration of gravity. So I shouldn't go at 1g, I shouldn't go at 1g, basically. But it turns out that you have to dominate gravity when you want to go up. And at this point is the maximum weight and the maximum load, and therefore at that point the controller gives up and encounters that singularity and cannot be computed. But the rest is just a linear design in terms of the state variables, because all these derivatives of the flat output are just functions of the state from the inverse of the differential parametrization. So you have, the problem is tracking F star, which you already defined. And because you know F star, you know F dot star, F double dot star, F3 star, and the precompensation. So if you want to deal with all these things, you can propose this linear controller for the auxiliary variable V in terms of F and its time derivative. So the tracking error, the velocity tracking error, acceleration tracking error, the jerk tracking error will be stabilized by suitable design constants alpha 4, 3, 2, and 1.